Okay. The general meeting rules for Peterborough Net Meetup is that we look to respect each other and their ideas. I'd ask that everybody can please go on mute, and with the exception of perhaps myself, if you could also turn your video off just to help any bandwidth or streaming issues we might encounter this evening. If you disagree with what has been said, please challenge politely at the end of the presentation, or please feel free to type away in the group chat as well if you've got any questions. These meetings are not for recruitment purposes. There's zero tolerance towards any discrimination of any kind. Also, zero tolerance towards violent, dangerous or criminal behaviour. Future presentation topics that could be covered. If anybody would like to do a presentation, then please get in touch with me. Always looking for willing volunteers to do presentations. So we're looking at perhaps F#. Signal R has been talked about in the past as a future presentation topic. Anything to do with Visual Studio 19, any command line tools that people use on a regular basis, any features, any hints and tips. Also .NET 5 and C# 9.
Fantastic. Thank you again, everyone. I want to say thank you to people for coming along virtually tonight, giving it your evening. I hope it's worth your time. Thank you also to Graham for arranging this and inviting me, and generally in doing the whole group. Group organisers are unsung heroes and often taken for granted. So I want to publicly say thank you for organising all this. I'm not a quantum computing expert. I am a beginner. Hope that doesn't disappoint anyone. If there are any quantum computing experts on the meeting, fantastic. I hope I don't get it too badly wrong. Please be gentle. Please let me know when I am getting it wrong. So, as Graham said, the basic outline is I'm going to show you some QSharp code now, some quantum computing code. Just give you an idea of it very briefly, and then there'll be a PowerPoint presentation going through the theory behind it, not plumbing the depths all the way down to quantum physics, but hopefully enough to give you an idea of what it's like, why this code is as it is, and also an idea of what you would need to learn if you wanted to get into this yourself, because there's quite a lot of learning prerequisites you would need to tick off before you got into quantum computing itself. So that's my aim for this evening. Please don't feel thick if you don't understand this. I said I'm only a beginner, and I've got to being able to call myself a beginner after going through the material at least 3 times, and it hurts my head each time. So don't feel thick. It's normal to find this stuff hard. And so please interrupt if you have questions. I hope I'll answer them either immediately or later on in the presentation. Right, that's enough preamble stuff. Onto the code. So this is a Visual Studio Code instance running on my laptop, which is a fairly normal laptop, nothing exotic. And so I downloaded Visual Studio Code, and I downloaded Microsoft's Quantum Development Kit, QDK, which is an extension to Visual Studio Code, and also copied some sample code from the Microsoft Quantum E website. So this is just a bog standard Visual Studio Code session. This code is written in something called QSharp, which is a Microsoft language. It's not a .NET language. You can call it from .NET, but it doesn't run on the .NET runtime, as far as I can tell. And the idea is, at the moment, I write this QSharp code, and I run it on my laptop, because part of the quantum development kit is an emulator that makes my normal hardware kind of act like quantum hardware, but much, much more slowly. And the idea is that when quantum hardware becomes generally available, I should be able to just lift this code and run it unchanged on proper quantum hardware, and it will go blazingly quickly. So I'm afraid I don't have quantum hardware to show you tonight. I think some vendors have it available on the cloud. So Microsoft isn't the only quantum game in town. IBM definitely do it, and I think AWS does it a bit. But it's really limited in all these situations. So I'm going to show you this QSharp code, and I'll run it first, and then we'll go through it. It's really quite short, so it shouldn't take too long. Just to show you that I have no tricks up my sleeve, I just did a clean. Now I'm doing a build. So this is normal stuff. It happens to be the QSharp compiler, but it is just doing build. This takes a little while. It's all good. And then I'll run it. So this is a random number generator, which will generate a random number between 0 and 50. In this case, the 50 can be changed. But between 0 and 50. Right, so that is quantum computing code that has just run on my laptop in front of you. I imagine you're rather underwhelmed. Sorry, this is the hello world kind of example, as far as I can see, for quantum computing. So if I run it again, I'll get a different random number. There we go. So we get a random number. How do we do that? Okay. So just a kind of overview before I delve into it. Yeah, this is QSharp, not C# or F#. It looks a bit like C# and apparently a bit like F#. So as the thing introduces a new namespace, these bring in other namespaces. It's a procedural language rather than an OO language. It says operation to mark a method. There's the return type, the operation name, and any parameters it takes are in there. So I'll go down to the bottom and work my way back up to here. So this is an operation that has been marked as effectively main. This is where execution will start. There's a constant being defined of max, given the value 50. And this is like console.writeLine. Looks very familiar with the dollar and the curly brackets. That's what you saw on the screen. And then it returns, and so we'll write to console the results of calling the operation sample random number in range, and the range is 0 to 50. So there's nothing interesting here except the fact that there is nothing interesting here. This is really normal looking code. There's nothing wacky going on. So just because it's a quantum computing language doesn't mean that every line is going to be weird and quantumy. You will blend classical computing stuff and weird quantum stuff. So the first two operations will be entirely classical computing that look like they're just written in a slightly unfamiliar language. So this is the entry point, and it calls, get me a random number, 0 to max. So I'll get that. And there it is. So it's taking max as an integer, an input, it returns an int as a result. Declare a variable output and initialize it to 0. And there's a repeat until to populate output, and then output is returned. And to temporarily forget the repeat until, so it declares an array of bits, and what this operator does is tell you how many bits there are in the binary representation of this integer. So it's log to the base 2 rounded up. So if this were 50, then you need 6 bits to represent 50. So this is saying it's like for each IDX bit in the range 1 to 6. And each time around the loop, it appends to the bits array one more bit, which it generates randomly by calling this generate random bit operator. So it will produce 6 random bits in an array, and then at the end, it will turn that bits array into an int and set it to the output. The reason why it's got this repeat until is it might overshoot. So if it comes in here with max being 50, it will say, I need 6 random bits. And 6 random bits could be all ones. And if they are all ones, then that's 63, which is too big. So it comes up with a random number, filling up the right number of bits. And if the value is too big, it just goes around again, starts from scratch. So again, this is just classical computing type stuff. Looks a bit unfamiliar in terms of the details of the syntax and the names of things, but I hope nothing too scary or weird. But it's this bit that is the actual quantum stuff. So we are finally getting to the quantum stuff, working our way up from the bottom. Oh, didn't like that. How do I delete that squiggly line? Has someone else drawn on that, or is that me? I'm sorry about that. How do I turn off that? Okay, it's gone. Good. Right, so this is the first and only operation that does proper quantum stuff. And it returns a bit 0, 1, which will be randomly 0 or 1. It takes no arguments, and it's really quite short. If you've used C# before, you'll be familiar with this using thing curly brackets construct. It's creating a qubit, which will also destruct when execution drops out the bottom of the corresponding curly bracket. So Q is a qubit, which we will get onto in due course. This H thing being applied to the qubit will make the qubit spit out 0 or 1 with equal probability. It's called the Adamar operator, this H thing. So the qubit is created without any predictable value, and then it's initialized so that down here, it will randomly spit out a 0 or a 1 with equal probability. And I'll get into the detail of that quite a lot in the presentation. And then this bit down here says to the qubit, please spit out a value. And at this point, it will spit out 0 or 1. The chances of 0 or 1 are equally likely, so it's a random bit, 0 or 1. So the qubit comes into existence here, is messed with by this Adamar operator, and then spits out a value, and then disappears. And that's one execution of generate random bit. And in the case where down here max is 50, that will mean this thing is called 6 times, each time creating a new qubit, doing stuff to it, and then getting a value out of it. So I'm not expecting you to be an expert in quantum computing by now, but does that basically make sense? I was planning to go on to the presentation now, but we can do a bit more on the code if you prefer. No? Cool, okay. Right, I need to do a bit of fiddling to share my presentation. Right, so the presentation is going to be in these 4 basic chunks. First chunk is really high-level stuff about qubits. So we saw a qubit in the code. I'm going to delve into that a little and contrast that with classical computing that you're already familiar with. Then I'm going to take a detour into bits you would need to understand that aren't strictly quantum computing in order to do quantum computing. Then a bit on quantum circuits, which is just another way of saying quantum computing code. And then finally, one example of an algorithm written using quantum computing called Grover's algorithm. So I'm going to start off with this contrast between classical and quantum computing, starting with some classical stuff that I hope is not new to people. So imagine you've got 3 bits, normal classical bits, not qubits. So normal bits can be 0 or 1, and they are these things A, B, C. So 3 bits, each having a value 0 or 1, gives you together 8 possible states, which I'm labeling 0 to 7. So hopefully that is all good news, familiar stuff to you. So I've got 3 normal bits giving me 8 possible states. And imagine you've got some normal classical computing code that moves the world from state 0 to state 1, 2, 3, and so on. So for instance, initializes those bits to be 0 and then just adds 1 a few times. Again, hopefully nothing weird. I'm going to start saying things that sound like I'm really laboring the point and concentrating on things that I don't need to concentrate on. That's to set up a contrast with quantum stuff. So you've got these 3 bits, and between them, they're all zeros, so that means it's state 0. And in the classical computer world, it's all lovely, and so the probability that the world is in state 0 is 100%. And the probability of being in any other state is 0%. So that's the weirdness. Why am I talking about it? Talking about it in that way, kind of thing. But we're in one state with 100% probability, and all other states have a probability of 0. And then we add 1 to the set ABC to move on to state 1. And we shift so that we are now in state 1 with 100% probability, and state 0, 2 to 7 with 0% probability. Again, nothing weird, just presenting it in a slightly weird way. And then we add 1 again, and the same thing happens. We're 100% likely to be in state 2, and 0% likely to be in every other state. So to kind of summarize that, what is happening is the code is directly acting on the bits to change what state they're in. And as a result, you would say the probability of being in a particular state follows on from what the code has done. So the code has moved the world into a particular state, and therefore the probability of being in that state is 100% or 0%. Again, a bit weird way of saying it, but it's to set up the contrast. And similarly, the world is always in exactly one state. There is a 100% probability that it's in that state and 0% probability of being in any other state. So that's all the classical stuff, 3 bits. We're now going to move into the quantum world. And in case people haven't come across it, I want to make sure people have heard of Schrödinger's cat. Schrödinger was a physicist who came up with this thought experiment to show quite how stupid and crazy quantum theory was. The idea was there was a sealed box, you couldn't see inside, a lid, and it starts off shut. Inside the box is a cat, a radioactive source, and a bottle of poison that's sealed. And if the radioactive source emits some radioactivity, that will break the poison file, releasing the poison and killing the cat. But you don't know if that has happened or not. And if you follow quantum theory to its conclusion, the cat is alive and the cat is dead at the same time until you open the box. So it's in these 2 states, equally likely, probability of 50%, until you open the box, and that collapses things down to either the cat is dead or the cat is alive. So I'll be using that a few times later. The idea is you have this quantum world in more than one state. There are probabilities attached to those states, but until you open the box or observe it or measure it, they're all kind of synonyms, you don't know which of those states it's actually in, and then observing it or opening the box fixes it, collapses all the options down to being in one of those possible states. So in the code, you saw qubit being used. And a qubit is a thing that can spit out 0 or 1. But that's when you measure it. That's when you open the box. Before that point, the qubit acts as a 2-element array. An element 0 and element 1. And 0 holds the probability that when you later open the box, the qubit will spit out 0. And as you would expect, element 1 holds the probability that when you open the box, the qubit will spit out 1. And these probabilities are visible and changeable, that's the important bit, without opening the box. It's like they're dials and knobs on the outside of the box that let you somehow change the contents in terms of what state is how likely, without fixing it into one of those states by actually opening the box. Okay, so a qubit, for most of its existence, won't have a particular value, but it will have these 2 probabilities that when you do finally measure it, you'll get 0 or 1. So if we had 3 qubits rather than 3 bits, so A, B, and C are now qubits, you have to think of them as being together in the same box. And because you've got 3 qubits, that gives you 8 possible states. And each of those states has its own probability attached to it. So before you open the box, you can fiddle with these probabilities attached to the states, as long as they together add up to 100%. So, and that makes those states more or less likely. So you can see that state 0 is hardly likely at all, state 7 is hardly likely, and then states 2 to 5 to be the most likely, state 3 and 4 are the most likely of all. So you can massage these probabilities with the box still shut, so that when you open the box, you are increasing the chance that it will spit out the value of the state that you're hoping for. So this is a fundamental difference between the classical world and the quantum world. Just to kind of summarize that in a different way, you can think of this as the life cycle of a set of 1 or more qubits. Time's going left to right, and you start off being in weird quantum land, which is why it's this fluffy cloud. What you do is you create the qubit. So remember back at the code, saying Q equals qubit, according to the constructor. You create the qubit, and you make it have probabilities that are easy to set up, or probabilities you don't care about. Still in weird quantum land, you do things to those probabilities so that you make it more likely that when you open the box, you get the result you hope for, and less likely that when you open the box, you get a state that you don't want. And in the sample code I showed you, that was that H symbol. That messes with the probabilities attached to the 2 states. In this case, sample code, it made them equally likely. So we still haven't opened the box, but we've been messing with the probabilities attached to the various states. And then we open the box, then we do the measurement. And at that point, things collapse down into one of the possible states. It's like the computer throws dice to work out which state that thing is in. And that's an extra bit of weirdness. That's the kind of top level weirdness, in that code is likely to be non-deterministic. It could be that the chance of getting the correct output is 92%, for instance, not 100%. So that your correctly written code, when passed correct inputs, will give the wrong answer some of the time. It could be that your algorithm can get the correct state up to 100%, in which case, brilliant, it's not non-deterministic. But that depends on the algorithm. And I'll show you later that there are some examples of Grover's algorithm where you aren't guaranteed the correct state will come out at the end. So your code will be non-deterministic. And that's interesting, is how do you test that it's correct? You start having to do stuff like stats, where you're doing significance levels and null hypotheses and all that kind of stuff. So you've got non-deterministic code, and that rests on interesting maths, which we'll be getting to shortly. And that interesting maths is a representation of brain-melting physics. So it's weird all the way down, I'm afraid. Right, so that's the overview I was going to give about qubits and their life cycle. Any questions on that? Otherwise, I'll carry on to some underlying theory. Okay, so on with some theory. A very good question. I hope I will show you how it has value when we come to at least Grover's algorithm, if not earlier. Sorry, I've moved my mic a bit closer to my mouth. Hopefully that will improve the sound. But also my Wi-Fi isn't the best. So I'm going to carry on to some underlying theory. One of the bits of theory is matrix multiplication, or matrices in general, but multiplication in particular. I'm afraid I don't have time to go through all there is to know about matrices. They're just a way of arranging numbers in grids and columns, that kind of thing. If you have this matrix, A, B, C, D, and you multiply it by a matrix, in this case it's actually a vector, it's only one column, then the rules are you just take a row from the thing on the left, the column from the thing on the right, and that gives you the corresponding bit of the output. So the first row, the first column, gives you the first row and column of the output. Second row, the first column, gives you the second row, first column of the output. And you just pair up corresponding bits, multiply up within the pairs, and add everything together. It may be that you've not seen that before. If so, sorry. You may be an expert, or it may be that, like me, you last did it about 30 years ago. So I'll just give you a concrete example, and then I'll move on. If you have the matrix 2, 3, 4, 5, and you multiply it by the vector 6, 7, you can see how it's taken a row by column to give the first row and column, second row, first column, gives those bits, and then you just do the multiplications, do the additions. So that is the final answer of that multiplication. Loads of places you can find online if this is new to you. This is matrix multiplication, sometimes also known as linear algebra. The next bit of wackiness we'll need, unfortunately, is complex numbers. And again, I last used these 30 years ago. Complex number includes the square root of -1. That's what this I is. Largely, you can ignore that for these purposes. What it means is each number has two parts to it. So the number that this thing is trying to represent is at the tip of the arrow. And there are two different ways of representing it, either in Cartesian way, which is like a grid reference on a map. That's what this thing at the top is showing. So the first number is left to right, the second number is up and down. So you'll see as this moves about, those numbers change correspondingly. The other way of representing it is in a polar form. This shows how long the arrow is, and this shows the angle that the arrow is making from this direction, straight out to the right. So you see it's making 90 degrees, 45 degrees, so it's the size of this arc. And it turns out that this form of complex number is the easiest for when you're adding up complex numbers. This form is the easiest when you're multiplying complex numbers. And the matrix multiplication I showed you before, which involves multiplying and addition, those numbers in a quantum computer will be complex numbers, unfortunately. So you will be doing these multiplying and adding of complex numbers. As well as these numbers reflecting what the arrow is doing, you'll notice this yellow shading filling up or not. And what this is doing is showing the probability that this complex number represents. So another wacky bit of quantum computing is probabilities. And instead of it just being a simple 0% to 100%, the way you get the probability out of a complex number is you square the length of the arrow. So square this value here. So you'll see that as the arrow gets longer towards the edge, this fills up. As it moves round, there is no change. Only the length of the arrow affects the probability which it represents. The fact that the angle is spare where it comes to probability is interesting. There will be times where we use this spare bit of information to slip a bit of extra useful stuff in without directly affecting the probability, but we'll be using it later. We've got it tucked in our back pocket for later. So the probability that the complex number encodes is the square of its size or amplitude. When you're adding complex numbers, so just do a bit on adding, a bit on multiplying. This is where the Cartesian version, the top version here, is easiest to use. We just add that bit to that bit, make that bit to that bit, give you that bit. Or if you prefer to see things visually, you are literally laying these arrows end to end. And as it happens, these follow suit, but you need to do some trig to work those out. So adding complex numbers, you look at the arrows that they represent, lay them end to end, the result is the result. When you multiply complex numbers, it's easiest to use this bottom representation. What you do is you add the angles and multiply the amplitudes. So you can see that, I'll go on to why this kind of animation is happening shortly. You can see that this angle is 45 degrees. This angle is half a turn less 45 degrees, and the result is 180 degrees half a turn. So you add the angles, and at the same time you also multiply the amplitudes. Given that this is representing a probability, we've got these shaded bits that are linked to the amplitude, and the probability attached to this is a half, the probability attached to this is a half. And so this is saying a half of a half gives you a quarter. And then, having made it come through in a kind of clear way, it just lets that quarter slump down so that its full width of height drops as it does that. So that's what's happening here. It's multiplying the two amplitudes together, and because they're less than one, we're getting a fraction of a fraction, so it's even less than one than it was before. So, you've got matrices, complex numbers, there are rules for multiplying and adding complex numbers. So when we combine matrices and complex numbers, you get this kind of thing. Now, this is a slightly weird representation that will make a bit more sense later. These aren't my diagrams, they're from a very useful site I found called Twisted Oak Studios. It's a software house in America, and they've got some articles on complex numbers, on quantum computing, rather. Back in the matrix multiplication thing I showed you, the matrix, the square thing, was on the left. The vector, the column, was on its right, and it produced a result further on the right. This has it slightly reversed, so that the vector starts on the left, and the result is on the right. This is because in a little bit, we will see values flow from left to right through a series of matrices. So this output here will become the input to another matrix to its right. I'm afraid I don't have time to go through the details of this, but I hope you can get the broad outlines of this, that this column goes to this row and this row. So this first bit in the column goes to the first bit in both rows, it's copied down there. The second thing in this column goes to the second thing in the two rows. This thin one will go here and here. It's down there. And then it's the multiply and add up bits as before. So it's a bit hard for the animation to capture all the details adequately. Please bear in mind that there are just numbers behind this. You can do all this in paper and pencil or on a spreadsheet if you want afterwards. But this is to show you how sizes of things are changing and the amplitude and phase and how they are changing as a result. So I'm not expecting you to fully grasp it from this. I hope it's enough for you to realise that there is a matrix of complex numbers and a vector of complex numbers being multiplied together following standard matrix multiplication rules, and you get out the vector of complex numbers. Right, so that is all the underlying theory I was going to go through. Next is starting on quantum circuits. Would anyone like me to go over any of the theory stuff again?
Bob, I'd say that I think there's some problems with your audio. It's quite crackly.
Oh, I'm sorry about that. I'm not sure what I can do about it. I've got my headset mic right up next to me, right up next to my mouth. My laptop does have a noisy fan sometimes. Try moving away from the mic. Is that better? I've now bent it away from my face. Is that better with it like that?
I think it was a little bit better when it was close up. Okay, yes, I'm saying it's probably a little bit better further away.
Is it better like this? I do know that when the fan gets going, it gets very noisy. Unfortunately, there's not much I can do about that either. So I realise how frustrating bad audio is. Unfortunately, I don't know what else I can do about it.
I think if you continue, Bob, if people have got questions, obviously they can post them into the chat. Perhaps is that okay with everybody?
Okay. Hi, Sean. Nice to have you here. Sean and I were colleagues for several years a little while ago, so it's very nice to have him. Okay, so we've done the introduction to qubits, their life cycle, we've done a bit of theory, matrices and complex numbers, and how complex numbers encode probabilities. Now we're going to go on to starting to build programs or quantum circuits out of all these bits. So if you think back to the example code I went through, there was that H function call or operation call that put the qubit into being equally likely to spit out 0 or 1. That's the Adamar gate. I think it's pronounced Adamar because it was invented by Monsieur Jacques Adamar, French mathematician. And it's represented by this H. So now hopefully you'll see why I've been talking about matrices and vectors. So the qubit is a vector of 2 elements, this 2D array, and the operators that work on it to mess with its probabilities, they are 2 by 2 matrices. And what this slide is showing is a very simple quantum circuit in 2 different ways. So the bit across the top, the horizontal line with 2 H's on, that's the simpler version of it, simpler representation. And that's what you'll see in diagrams online and in books, that kind of thing. And then the bottom bit with the ons and offs and so on, that's a bit of detail behind the scenes that is unpacking the top line a bit. So what this is showing is if you start off with your qubit, that's what this wire is showing, the horizontal line. If you start off with your qubit being either 100% going to be off or 100% going to be on, when it goes through the Adamar operator, it will come out equally likely to be on or off. But it doesn't matter if the thing comes in 100% on or 100% off. It will be spat out as 50-50 on and off. And also, it shows a wacky property of the Adamar operator, which is if you've got that 50-50 state that could have come from either on or off, if you put that through the Adamar operator again, somehow it knows how to unscramble that back into 100% on or 100% off. So the stuff moving across the screen that's shaded red corresponds to something that came in as 100% on. The thing that comes in shaded blue is something that came in 100% on. And don't forget that the shaded bit, the red or blue, is the probability associated with that cell. So you see the red thing comes in with the red all in the bottom cell, and then the red is half and half in both cells. It goes through the right-hand Adamar, and we're back to 100% in the bottom cell. Similarly, you need to wait a little bit for the blue to start on the left-hand side again. Comes in with the blue 100% in the top cell. Goes through the Adamar, and it's 50-50. Goes through the Adamar again, and that 50-50 turns back into 100% in the top. And you might think, that's witchcraft. How can the second Adamar know whether this 50-50 mixture it's receiving came from on or from off? And this is where the probability only using the amplitude and not the phase comes in. So the phase is this bonus bit of information. If you look at the arrows in the middle now, the blue thing, they're both pointing to the right. And then look at the red thing when it's in the middle. Look at its arrows. One's pointing to the right and one's pointing to the left. So the two 50-50 probabilities, whether they came from red or blue, aren't identical. You can tell by the phase, the combination of phases, where this thing came from. But if you were to measure the qubits in between the two Adamar gates, the came from on version and the came from off version will behave identically. They are equally set up to be 50-50 on or off. So this is the first little bit of code represented as these boxes. If you chopped the screen in half, you've got rid of the right half. That was the top operation in the sample code I showed you. You get a qubit, put it through the Adamar, and then you measure in the middle now, and you get 50-50, 0, 1. This quantum circuit, this program, just for the sake of it, isn't measuring at that point, it's putting it through an Adamar for a second time, so you unscramble it by using this extra information of phase. So I'm aware that I'm showing you some kind of interesting stuff that isn't obviously valuable yet. Bear that in mind. Promise you I am working towards that. So what this is showing is a single qubit, a single wire going across the top of the picture. You could have more than one qubit. This H2, that's just an Adamar that can operate on 2 qubits at once. So 2 qubits gives you 4 possible states. What the bottom half is doing isn't showing you all 4 possible states, it's just picking both ons, the top line, and both offs, the bottom line, as just representatives of the 4 states. And the same kind of thing is happening as before. You see that the red one comes in the middle, its arrows are a mixture of lefts and rights. Whereas the blue one, when it's in the middle, its arrows are all rights. So that the right-hand Adamar does have enough information to unscramble that jumbled up bit of the middle back into its original 100% in one slot version. And another small difference, just being consistent, is you'll see that in the middle, states aren't 50-50, they're 25% each. There are 4 states, each having to share 100%, so they're at 25% equally likely. So in general, the Adamar gate makes all the inputs equally likely, sorry, all the states equally likely, which might be 50-50, might be 25 times 4, etc. So that is an example of quantum operator, the Adamar. There are several others, which I won't go into. You can find them online. There are about 10 of them. And they'll each be implemented as a matrix of complex numbers. And quantum code will be made by pushing qubits through these quantum operators in the right order, right combinations of them, and so on. Now you might think, again, well, where's the magic? I was told that quantum code was really quick. You know, it would break cryptography trivially quickly and all that kind of thing. The secret comes down to these matrix multiplications. So if you think back to when I spelt out all the detail of the matrix multiplication, and that was only a 2 by 2 matrix with a 2 by 1 vector, there were quite a few little multiplications and then additions to do one multiplication. And as the matrix grows, and the vector grows, then the number of operations you do goes up exponentially, or quadratically. So if you were to do these matrix multiplications on a classical computer, the more variables you have, more bits, the bigger your matrix and so on, your code would run quadratically slowly because of all the stuff you'd be having to do, all the little bits of maths. The secret sauce of quantum computing is the operation of multiplying the matrix and the vector is a single thing. It costs 1 unit because of quantum physics doing the hard work for you. And it doesn't matter how big your matrix is, how big your vector is. Multiplying the matrix and the vector together costs you 1 unit of time because quantum physics is doing the hard work. So if you're able to come up with an algorithm based on this matrix maths, and as a course, in the course of running all these vectors through all these matrices, you get the probability of the right answer to be high enough that it's worth doing. Then you end up with the right answer enough of the time and more quickly than you would get it if you did it with a classical computer. So that's why there aren't all that many quantum computing algorithms at the moment. You have this relatively limited set of building blocks, and what you're aiming for is actually quite hard. You want to have the correct output enough of the time, hopefully 100% of the time, that it's worth doing the hard work. So we've done qubit life cycle, the theory that's off to one side, a bit on quantum circuits. So now I'll go through an example algorithm, which is Grover's algorithm. And Grover's algorithm was the second of the big algorithm suite to be discovered in quantum computing land. First, Shor's algorithm. It was only invented in 1996. It shows you how recent all this is. And what Grover's algorithm does is, if you've got some function where one input will produce a particular output, so for instance the value true as the output, and all other inputs will produce some different output, so for instance false, it finds the one input value that will give you the one output value you're after. Okay, it's a slightly special purpose kind of algorithm, but it's a relatively easy one to talk about. So that's what we're going to be talking about now. And if you had a classical algorithm to do this, sorry, Chris, a question. Yes, absolutely. If you're comfortable with the big O notation, the classical way of doing a matrix multiplication is big O m times n, where n is the size of the matrix, n is the size of the vector, and it's now going to big O of 1. Absolutely. Thank you, Graham, for pointing it out. So the classical algorithm, on average, will take n over 2 steps, where n is the size of the set of inputs. So if your method, this mystery method, can take 100 different inputs, as in the numbers 1 to 100, all you can hope to do is start at 1. Is it that one? No. Is it 2? No. Is it 3? And you work your way through them one at a time, and on average, you will reach the magic number halfway through. Some of the time it will be the first, some of the time it will be the last, and that averages out to halfway through. So classical algorithm will take of the order of n over 2 steps to find this one value you're after, where n is the size of the set of all possible values. Grover's algorithm isn't blindingly fast. It takes pi times the square root of n divided by 4 steps. So the key part of that is it's the square root of n rather than n. So it's a quadratic improvement. And as I said before, this is based on the fact that a matrix multiplication is a cost of 1, a big O1 operation in quantum land. So you have to jump through a few mental hoops, unfortunately. So I said this is a mystery function, and it's somehow going to be used in the world of a quantum circuit. Well, the only thing you have in a quantum circuit is a matrix that acts on qubits. The qubit is the input, or some set of qubits is the input, and this mystery method is some matrix that will do stuff to that vector. And so if you think about your vector, that is your set of qubits, like with the red and the blue things we've seen in previous slides, you can think of it as if I pass in to this mystery method a qubit so that it's 100% likely to be in one of the states, that's what it refers to here as a classical state. So if it's definitely in one of those states that the qubits can represent, and if that state isn't the solution, then this mystery function will spit out false. False will be encoded as you get the input passed out without being changed. If the input is a classical state that is the solution, then true is encoded by the output being the input, but rotated by 180 degrees. So the phase is going to change by 180 degrees, the amplitude will be kept unchanged. Okay, so that's how we're representing this mystery function in the world of a quantum algorithm. So we're representing true as output becomes 180 degrees rotated. False is represented as inputs pass through unchanged. I realize I'm kind of simplifying and constraining this problem a lot. Sorry, that's just the nature of this algorithm. What this means is the mystery function will be a matrix where everything is 0 apart from the diagonal going top left to bottom right. And this diagonal will be 1 plus 1 everywhere, apart from one of them will be minus 1. And essentially what Grover's algorithm is doing is finding where this minus 1 is. And you might think, well, it's blindingly obvious, it's there. And yep, I accept that on this diagram, it's blindingly obvious that -1 is here. But it could be that this is 65,536 elements, top to bottom, and the same left to right. So you've got 65,535 wrong answers, but only one right answer. And you could linearly go through this, and that's what the classical algorithm would do. And on average, it would take you half that, so 32,768 steps to do it. Grover's algorithm would find this -1 more quickly than that. It would find it in roughly the square root of 65,536 steps, which is 256. Okay, so that's what Grover's algorithm is going to do. You pass it a matrix like this, where you as the human code don't know where this -1 is, and it will spit out a vector where ideally it will say 100% probability here, where the -1 is, and 0 probability everywhere else. So that's what we're aiming to implement with Grover's algorithm. Something that spits out classical state that corresponds to where this -1 is. And again, this isn't my diagram, so from the Twisted Oak article on it. So this is the unknown matrix, and you'll see that it's zeros apart from the diagonal, and this one is pointing that way, that's the -1, and the others are +1. And what's happening is an Adamar operator happened here, so that everything comes in equally likely. And then you see that the phases are rotated only where that was. And then you put it through this matrix, and that uses the difference of phases to shuffle the probability away from the states you don't want and towards the state that you do want. Now this case, where you've only got 2 qubits, so you've got 4 possible states, you get 100% likely output after one pair like this, with the unknown thing, and then this amplifier matrix. Unfortunately, that isn't always the case. As you get more qubits, you need more steps. So this one, there are 5 qubits. There's an Adamar up front to make more equally likely. And then you repeat that thing from the previous slide, the mystery function and then the amplifier. You do that 1, 2, 3, 4 times. And you can see that at this point, the states are equally likely. And then at this point, it's 62% likely that you have off, on. One of the classical states that you could get. And then after the next one, off, on is 79% likely. The remainder percent is spread out elsewhere. And after this one, it's 95% likely to be off, on. And then after 4 goes, it's 100% likely to be off, on. So you can stop, you can do the measurement here, and the correct classical state will come out. So that's it with 5 qubits, and this shows how many steps you need for different numbers of qubits. So little n is the number of qubits, big N is the number of states that those qubits can encode, And then this is, after doing that repetition, how many times, how likely is the correct output to be? So that off, on state was the correct output in that particular example. And that was in 5 qubits after 4 steps. Actually, sorry, I think that was indicative. I think this is correct numbers. But the interesting thing is the values climb. So when little n is 6 qubits, you need 7 repetitions. But there are 2 potential problems. If you go with 2 qubits, after 2 steps, you get a nice result. But then going too far will make the right output less than half likely. And then it goes back up again. So there's some maths that will tell you where the first peak is on these graphs. So you need to know how many qubits you have, and therefore how many steps you need to do to get the highest probability. Another potential problem is that these graphs don't all climb to 100%. So when you have 4 qubits, you will get the right answer after 4 steps, but with only 96 or so % probability. You'll get the wrong answer 4% of the time. And that's just the way it is. That's what the maths says. Unless someone can come up with a different algorithm where it's 100% for all numbers of qubits, this is the best that there is. So I'm aware I've skated over Graham-Whitmer's algorithm. No, these steps are executing in series. So, wrong way. So it really will go, apply the ADMAR, apply the mystery method, and then the amplifier, mystery step, amplifier, mystery method, amplifier, mystery method, amplifier. But each of those is a matrix multiplication, which is of order order 1. So you've got 5 qubits, so that's 32 states, and so here it's doing. I'm not sure if it counts this as a step or not because it's constant. You always do this no matter how many qubits you have, but so for 32 possible inputs, you need to do 4 serial steps. But only 4 serial steps. You don't need to do 16, or worst case 32. So that is the speed up that the quantum is giving you, because these steps are relatively cheap, and you only need square root of n of them rather than n of them. And I'm afraid I haven't read all that far about it, but I get the impression that other quantum algorithms produce a bigger speed up. There will still be a series of steps you go through in series, but that series of steps is shorter by a bigger margin than the corresponding steps you would do in classical computing. Right, well, as it happens, I've run out of slides. All I have left is yes, the steps need specialist hardware. At the moment, the steps are implemented in the emulator, possibly using my laptop's graphics card to be a bit faster. But you need the specialist hardware to do them, because if you remember that things like the Adamar operator are messing with the probabilities of the states before you open the box. So somehow, from the outside of the quantum weirdness box, you can do things that influence what's going on inside the quantum box. And I think that's where the specialist hardware is needed, and they're very clever people with quantum physics PhDs and big research budgets. And another thing where I've kind of skated over is the underlying quantum phenomenon behind all this is superposition. So the way in which you can have more than one state likely before you open the box. That isn't the only quantum phenomenon that quantum computing can use. I haven't gone into those, but there are things like entanglement. I didn't want to hit people too much in one go. So just to summarize, this is weird all the way down. You have non-deterministic code that rests on wacky maths. Complex numbers are a bit of a brain bender, and that is an encoding of wacky physics. So it's weird top to bottom. The secret sauce, at least for superposition-based algorithms, is this quick matrix multiplication. The interesting thing for me is the result that you get at the end. That's the data as far as you, the end user, is concerned. But for most of the time, the code doesn't deal directly in that data. It deals with the probabilities of different options for that data. And those probabilities are effectively metadata. They are data about the real data. So the code deals in metadata for as much as the time as it can, because that's the quantum bit. And as late as possible, it then turns metadata, these probabilities, into data, the actual value. That's at this measurement or observing or opening the box time.
Can I start by saying thanks, Bob? The audio made it a bit difficult, but what you were saying was sort of so clear that we got through it no problem.
Thank you.
I thought you might be talking about entanglement and all that sort of thing. Everything that you've said, all this matrix manipulation and so on, that's all new to me. That's how this quantum computing worked. And it makes a bit of sense. Now you've taken us through it.
I'm glad. I think there is a separate world of pain where you use entanglement in your quantum computing code, because I hadn't found a proper beginner's guide. I've had to reverse engineer this from a lot of painful detail, with lots of alien notation. So there's the Dirac notation, the Bloch sphere, complex conjugates in matrices, etc. So I was aware that there's serious yak shaving you need to do if you're not careful. I don't know if you've come across the phrase yak shaving. It's where you get sidetracked on subtasks, which in turn have subtasks and subtasks. And it's a kind of shaggy dog story, which has the kind of punchline. So that's how you found me in a zoo shaving a yak.
Right. No, it's not a story I've heard. But
Right. So
I recognise the going down rabbit holes.
Yes. So this is a landscape littered with rabbit holes of pain. So.
Well, I'm really glad that you've persevered this far.
I hope I haven't misled people into thinking it's easy. I wanted to give people enough of a flavour so that if they were able to see if it was an area they wanted to pursue or not, and have a framework for that further study. I'm afraid to understand it all, let alone create your own algorithms, would take quite a lot more effort.
I think you succeeded very well there, Bob. It doesn't look
very
easy.
Sorry, I succeeded in making it not easy or in making it easy?
Not easy. What I'm intrigued about is that the quantum states themselves, at least the supercomputers I'm aware of, are based on actual physical, sometimes down to actual atoms, the states of atoms that is measured by magnetic fields and so on.
Yes.
So maintaining the quantum states at that level is very, very hard. So
yes.
How error prone is all this? In other words, is Einstein wrong that if you do the same thing twice, you get two different answers?
I think that's why it is still in the lab and not widely distributed, because it takes hardware problems to be solved first. And the thing that I haven't wrapped my head around is the mapping between arbitrary series of things in your quantum code and limited physical things with mystical quantum properties. Now, how do you get a qubit to flow through an Adamar gate 3 times? Do you need 3 Adamar bits of hardware, or can you reuse one Adamar thing 3 times? But how can you get it looping while maintaining superposition? All those kinds of questions I haven't understood. So as I said, I really am a beginner with this. So many questions I have unanswered. The reason why I got into it is I listened to a podcast called Data Driven, which is about machine learning, artificial intelligence. It's just a way for me to keep tabs with that world. And one of the presenters of that, a chap called Frank Lavinia, has got all excited about quantum stuff. He works for Microsoft and has started a second podcast called Impact Quantum, where he's going into quantum stuff, but at a what does it do for society, what's the business impact kind of level. And he exhorts people to just have a go. You can download the QDK for free onto your laptop and just have a play. So I thought, how hard could it be? And it turns out really quite hard.
So the emulator bit is very straightforward, but the concepts and the how they do it, the real thing, is a different story.
Yes, yes. And getting the skill of playing with this new set of Lego bricks. It's a completely different set of Lego bricks to what you have in classical computing. You have to know what these magic matrices can do, and then how to string them together to get the outcome you want.
So does QSharp come with a set of, did you say about 10 operators?
I believe so, yes.
Right.
I've been trying to find details of the operators in QSharp online during the break, and I couldn't find it. The general quantum computing literature has standards. You know, this operator is always represented by this letter. So if you find stuff from one website and learn from that, you should be able to go to QSharp and play with it. I get the impression that because this is all coming from the same quantum theory, there isn't a lot of incompatibility like there might be with different flavors of SQL between database vendors.
Yeah.
Is there, apart from solving classical computer problems much faster, how many quantum problems are there that can be solved that classical computers just can't solve?
I don't know, sorry.
Just thinking, like, you could have wave interference type problems that sort of the classical.
I'm aware that there are that some of the recent advances in quantum computing have been very specialist, in that they solve only a very tightly defined problem, and they do it with very special purpose, interesting hardware, and those have seemed to be quantum problems being solved. So it's not creating a general purpose quantum computer to solve a particular quantum problem. It's coming up with a special purpose bit of quantum hardware to solve one quantum problem. So I've read a couple of those in the last month or so. And that allows the people involved in those projects to make a big noise about how fast this thing is and how amazing it is. And those statements could be true, but it's very limited applicability because it is solving only this one particular quantum problem rather than it being a general purpose maths engine.
Right, that makes sense.
Bob, can I ask, your sample code that you showed at the very beginning,
Yes.
in VS Code, you apparently newed up a single qubit.
Yes.
Would the power of your laptop be able to new up more than one qubit?
Good question. I don't know. Trying to remember what I tried doing my own bit of code rather than copying an example, and I seem to remember it struggled beyond 3 or so, because the state space is doubling with each new qubit.
Yeah.
So the memory, the model it's having to maintain in memory is doubling each time. In the break, I've changed the sample code, so it's now newing up 6 qubits. I haven't run it, but that you can feed all 6 qubits into one Adamar. So the language supports multiple qubits. I don't know if my laptop So I've got, instead of just H brackets Q, as an example, I've got H brackets Q, comma R, comma S, comma T, comma U, comma V.
Okay. So it's taking that as a, so the H operator is taking it as a almost like an open-ended params, essentially,
Yes,
in that way.
or,
Yeah.
or it could be maxed out at 16 or so, you know, some nice arbitrary, slightly biggish number, but I haven't hit it yet.
It'd be interesting to see how the emulator represents a qubit.
Yes, I expect very clever people at Microsoft Research have worked very hard on it.
Yes. I hope you're going to give this talk to other audiences.
Well, thank you. You are the guinea pig, so I haven't been invited anywhere else yet. Graham was foolish enough to invite me, so who knows?
It's been a really, really good presentation. I think my head, at the break, I was saying to my wife, I think my head is hurting me a little bit. It was just really deep, pure maths, essentially, and statistics, and I had a bit of a headache. I had to have a glass of water.
I'm in some ways, I hope you don't take this the wrong way, in some ways I'm very glad you said that, because when I've been going through this, it has been uniquely painful. You know, if I'm learning a new graphics library or a new technique for sorting or something, it might be hard work, but I'll get there in the end. Whereas this seems to hurt my brain in unusual ways. I think in the ways that you've just described, that you're fighting this mental battle on so many fronts at once. You know, you've got to get the complex numbers completely down pat, so they're as natural as tying your shoelaces. Oh, and some matrix stuff, and probabilities. Oh, and by the way, you've got to put some quantum stuff on the top of all this. It's a really iterative process where you do one breadth first traversal across a very high up level in this tree, and that's all your brain can cope with. But once you've got all the way to the end, you've got that version of the big picture, and that gives you just about enough to do a breadth first traversal one layer deeper. And that's painful again, but you've managed to get that lower level down, and you just keep going level at a time. Sometimes more than one go to give them a level because it hurts so much.
I've got one more question, if you don't mind.
Yeah,
Don't mind,
please.
Bob. Going back to the, I think it's pretty much near enough the last slide you had in your slide deck, where you showed for the most efficient number of steps.
Yes.
For given various number of qubit calculations, there didn't seem to be much of a pattern to that. So, for example, for 2 qubits, it was 2 steps was the optimal number of steps to take to get to the highest probability level.
Yes.
But for, I can't remember if it was 5 or 6 qubits, then it was 6 or 7 steps. Didn't seem to have any sort of rhyme or rhythm to if there was a pattern on or something.
There is. Trying to. No. Do I need to be made?
Oh, shall I set you back as host again? Yeah. Hang on a second. Oh, how do I do this? It's not giving me the option when I right click on you, Bob, on my screen to set you.
On mine, he's already set up as the host.
Oh, okay. So I think you can just start hosting again. Thanks, Teffa.
Yeah.
Cool. Complete user error. I can't. No. All I can see is a small picture of you, Graham. I can't get to the bigger.
I do apologise for that.
Ah, no, there we go. Right, sorry, I've getting there. Sorry for the. Can you see a PowerPoint presentation?
Yes.
Right. So this is the graph you're talking about.
Yes, this one. Yeah.
So as little n and big N increases, the number of steps for the first peak also increases.
Mm-hmm.
So it's 2, 3, 4, 5, 7, and 7. I think there is a relatively straightforward equation, and it may be doing some rounding to the nearest number of steps.
Mm-hmm.
And hence this one, this one actually peaks here rather than here. You've got two curves peaking at 7 and none peaking at 6.
Yeah, I guess it would make sense that there's some equation that determines the optimal number of Grover steps. And is that based on a Grover? Forgive me if I got it wrong. But a Grover operation. Is there other operations that are perhaps more optimal given the number of qubits that you're working with?
As far as I'm aware, to solve this problem, Grover is the best game in town.
Okay.
But to solve other problems, you use different.
Okay.
These diagrams are all from this twisted oak. If you search twisted oak quantum, you'll find it.
Mm-hmm.
Were there any other bits of the presentation you'd like me to get back to?
Right, Sean's dying. I have to leave at 9, I'm afraid. So can I say thanks ever so much to you, Bob. I do hope you do this for other people. And thanks, Graham, for organising.
Not a problem. Thanks again, Bob.
Yeah, thank you. I've absolutely enjoyed.
Thanks.
Excellent. I'm glad.
Have a good night, all.
Okay. Bob, can I ask you just to transfer me back as the host? Is that okay?
Certainly. I'm trying to work out how to do that.
I'll also stop recording now as well.